Okay, so looking at linear models, it's the first model we're actually going to consider by itself. We're going to talk about all of the models that we discussed earlier. But linear models, we can look at them in tables, graphs, equations, and they are examples of mathematical models. So a mathematical model allows us to represent the relationship between real-world quantities, analyze behaviors, and predict future behaviors. Pretty much what we're talking about is mathematical models allow us to represent real-world situations mathematically so that scientists and analysts can look at what's going on and try to better predict what's going to go on in the future. A great example is what's been going on with the COVID-19 numbers. We represent this mathematically, and analysts and scientists are then able to predict what's going to happen in the future. Okay, they're predicting right now a constant decline due to the vaccine, and they're looking at potentially people loosening their restrictions and things like that, which may make us have an increase in numbers. And they're using all of these mathematical models to represent this so that they can get actual numbers and predict accurately what's going on at the next step. So for a linear model, you're going to need to be able to represent it from a table of values. So that's looking at the first differences. From a graph, it's a straight line, or from an equation, we have y equals mx plus b, where m is our slope or our rate of change, and b is our starting value or our y-intercept. Okay, so we're going to talk about that a little here. So analyzing the graph of a linear relationship, the vertical intercept, so the y-intercept represents the initial value of the dependent variable. The dependent variable depends on what's going on. Okay, independent variable is almost always time. Dependent variable could be more or less anything else that you're considering. Going back to the COVID-19 example, dependent variable would be the number of cases or the number of deaths or the number of recoveries, things like that. Those are all dependent variables, and we can graph all of those over time. The slope would be the change in the value over time. So the increase of deaths or the increase of cases or the increase of recoveries, things like that. Okay. Again, vertical intercept starting point. Y is our dependent variable. M is our slope, and X is our independent variable. For our example, that's time. Okay, that's the thing that can't change. All right. Again, if we're looking at this on a graph, and we had this example before, and I said when I do this, I like to go up first and over, but a lot of textbooks are going to show it to you like this. You need to recognize when you're finding slope, you're always doing the change in y first divided by the change in x. Okay, it's the rise divided by the run. All right, here are some examples for this.